Morning, everyone. So we're officially into new stuff. This is actually the start of our IB12 chemistry course. We're going to be going through four main chapters in this first part of the course here. First chapter is the one that we're beginning today. This is going to be Unit 6 as a continuation of what we did in IB11. Unit 6 is a chapter on reaction kinetics. Essentially, what we're interested in is when we're studying the kinetics of something, we're studying the speed of a reaction. We're studying why some reactions are fast, some reactions are slow, what that speed depends on, and therefore if I can figure out what the speed depends on, if I can speed up reactions or slow down reactions accordingly. We're going to find that the first four chapters that we go over in IB12, it overlaps really closely with the regular grade 12 curriculum. Afterwards, we're going to do a new section on organic, a small section on spectroscopic, and then we'll finish off our year with options. So without further ado here, we're starting off into our new chapter on reaction kinetics. The key idea with reaction kinetics here, reaction kinetics is the study of rates. You can think about this, the rate is to describe something, how fast a reaction occurs, but not how far. How far has to do more with completion, has to do with does the reactants 100% become products, does it hit an equilibrium, whatnot. We are interested this time in the speed versus in chapter 5 we were looking at spontaneity. We were saying free energy change is negative, it will go 100%, right? Spontaneous reaction. We're not looking at the how far anymore. That was more so chapter 5. We're now into chapter 6 for the how fast. So let me introduce the main concept throughout this chapter here. For reaction kinetics, we're studying the rates of a chemical process. So in general here we have reactants here on the left side. We're going to draw an arrow over to the product side. The reactants are becoming products. And what we want to study here is what's called the rate of reaction. If they ask you to define rate of reaction, you cannot use this term rate. You can't be like, oh, it's the reaction rate. Right. You need to find some other way of describing it here. We're going to say here the rate of reaction is a measure of the speed. You can't even say the speed of reaction, right? Let's just qualify that a little bit. The speed at which we can say product concentration increases because products are going to be made, or you can call it as the concentration at which the reactants decrease. Sorry, I forgot to mention, you're going to find a digital copy of these notes here. I would encourage you just to print off a set and then just scribble over as we go through here. So in that case there, because we're measuring these changes, we can write this in two ways. We can write rate. The rate of reaction here is the increase, so it could be a positive number here. We're going to use a delta symbol for change in. We're going to watch how the product concentration increases over time, or just to indicate that the reactants themselves are decreasing and they're getting consumed, we can actually just use a negative. But again, we're tracking the change in the reactant concentration. As my reactant particles start disappearing and start colliding away, this one here will start decreasing. In terms of the units here, because we are generalizing and we're using this terminology of concentration, the units on the top here would have been mole per dm cube, right? So that's equivalent to a molar, and then we're going to do a per second. So usually this is shorthanded all in one line here, mole per dm negative 3 and seconds to the minus 1 there. Okay. We're going to find throughout the section here, because rate here is a measure of the speed of reaction, rate is always proportional to 1 over time. So if our reaction takes a long time, right, the seconds is a really big number here. 1 over a large number here would mean that the rate is overall really slow. In this case here, time would be in seconds, so therefore rate is actually measured proportional to seconds to the minus 1. Right. So there we go. That's how we introduce rate here. Again, just the keynote here is when you're defining rate of reaction, you cannot just say, oh, it's the rate at which the reaction occurs. You have to say something along the lines of it's a speed, and how do you describe reaction is when you convert reactants over to products. Now, in terms of wording here, we know we actually do produce products, so we can say it's the rate where products are formed. We can keep that as a positive number here. You can use terminology like for reactants here, you can say it's the rate at which reactants are consumed. Consumed means used up. if in the wording we're sort of already implying, oh, I'm actually going to lose it here, I can still treat this, oh, maybe I lose my reactants at 5 molar per second. I can treat that as a positive number, but just remember consume means this thing here disappears. So therefore, the negative sign, just by convention, the negative sign in the reactant expression talks about this one here decreasing for reactants, but by convention, we usually just state it as a positive value. So we usually say, okay, my reactants, let's say, for example, my reactants are being used up at 5 mol dm negative 3 per second. In the math, it might come out as negative 5, but I can still quote it as I'm consumed at a positive 5. This is what's being lost. Right? So just a little bit of convention for you here. First part of this is we're going to just find a couple different ways we can actually measure the rate. So not even talking about what the rate depends on or can we change the speed. This is just a simple measure of how do we find out what the speed is. Although in general, in our definition, we had said sort of concentration, it's how much product I make, it's how much reactants is consumed. Depending on the property that I'm looking at, sometimes we're not really talking about concentration. Sometimes what we're going to do is we're going to track maybe a volume that's being produced or a mass that's changing. So technically, you could actually change this top part. If you just generalize a little bit here, the rate just describes you're watching some physical amount change in time. Of course, if it is concentration, the top unit being concentration makes sense, but just for completeness sake here, if we have a change in volume, I can go, how many liters do I produce per second? If it's a change in mass, I could go grams per minute, something like that. The key is the bottom has to be some unit in time, right? So here's just a walkthrough of some properties I can look at, and it just sort of generalizes how do we find this rate here. First one here is change in volume. Whenever we talk about volume and pressure, we usually specifically talk about gases. Gases are compressible. We know from the kinetic molecular theory, the particles are already wildly separated. They're just sort of colliding every which way. They're going to respond. We know that volume and pressure are opposites of each other. These are inversely related. If you increase the pressure, you're squeezing this balloon here tighter and vice versa. So in this case here, we have a change of volume of gas produced. You'll notice that over the course of the reaction, this is taking a piece of magnesium, maybe a magnesium ribbon, dropping it in hydrochloric acid. It's a typical property of acids that it reacts with metals, so you're going to actually see bubbles forming. The products actually imply to us that magnesium chloride is fully soluble, so magnesium chloride sticks around in solution, but we actually start generating one gas as a product. This one here is a gas. As we start creating those bubbles of hydrogen, it's going to then release into this container here. For the moment here, we can refer to this system here as a closed system, because this closed system, in this case here, matter can't escape. We actually sort of, if I had a complete lid here, all the hydrogen would stick around. If I put this on a mass balance, the mass number wouldn't change. However, what I do here is I actually hook it up to a syringe. This is a very special syringe that maybe I start off, maybe my syringe marked off at 0 milliliters. As the gas gets produced, it gets sort of shunted down this tunnel here, and slowly the syringe gets pushed back. I have little tick marks here on the syringe, and I can actually track in real time how quickly this gas is being released. If the reaction rate is very fast, it's going to push the syringe really, really quickly. If it's much slower, the syringe still pushes back, but it takes a little bit of time for that to happen. So in this case here, for volume of gas here, we can say we can measure the change in volume of gas at regular time intervals. You can eventually plot this out on a graph to sort of interpolate the pattern between when you actually take a measurement. You can do it in 5-second intervals, 10-second intervals. It really depends on the reaction. So in this case here, the equipment needed, we're going to use a very special type of syringe. Basically, it can slide larger and larger as the gas is being produced. Use a gas syringe, or we did an IB11 using an inverted burette. If you remember that experiment there, that was, we had a big water tub, and then we had a burette filled completely with water. It's the air pressure that's actually keeping the water inside. As we, in a similar fashion, bubbled the gas here into the tube, that gas there started pushing the water out. I can actually make readings of how the volume changes in time. I would probably take down some readings, let's say at which time intervals I'm looking at, what does the syringe say, and then I would eventually plot a graph of volume versus time, and we'll study this graphically afterwards. One important note here, not immediately obvious, is this notion, it's important for this reaction to only be producing one gas. let's say hypothetically that this MgCl2 was also a gas. It's not that the syringe wouldn't be pushed back. It's not that you wouldn't be able to measure in time after every 5 seconds, every 10 seconds, how does the volume change. What we're going to see is eventually when we actually quote a rate, it's really useful if we only have that rate specific to one chemical. If I know that this syringe here is being pushed back, the increase in volume is due to hydrogen, I can actually use my mole ratios again. I can actually stoichiometrically re-express it in terms of other chemicals. If both of these were gas, yes, the volume does increase, but I don't know how much is attributed to MgCl2 or how much is attributed to hydrogen. I wouldn't be able to do the stoichiometry I want afterwards. So keynote there is you want to do one gas. Second case here is a change in mass. So they hint at another reaction. We're taking calcium carbonate. This is actually just sidewalk chalk. We're going to drop in an acid again. Acids have usually been diluted in a bunch of water, so aqueous. This becomes calcium chloride. Water, again, it releases one gas. You could totally set it up in the same way that we did earlier. In this case here, unlike a closed system, which is sort of completely sealed, the gases can't escape, we now at this point here have an open system. An open system is one in which matter can escape. So what's going to happen here is we're actually going to sample the mass of the entire system. This is a fancy electronic scale here. We have our hydrochloric acid. I drop in our little pellets of calcium carbonate. We can talk about surface area as a factor later on, but basically the same thing. Hydrochloric acid is going to start, there's a double replacement reaction that occurs. It's going to start breaking up the chalk, and it's going to produce carbon dioxide gas. This time, because we are in a completely open system, as the CO2 actually escapes, we're going to actually find that this mass is constantly decreasing. So as I track the mass over time, let me just make up some numbers here. Let's say at first, at 0 seconds, so this is my initial rate. At 0 seconds, let's say my mass, beaker plus the calcium carbonate plus the water, let's say it was 100 grams. And then what I can do is, as the carbon dioxide gets released, we're in an open system, the gas there escapes. Maybe I sample it again at 5 seconds, and maybe now it's down to, 94 grams. Maybe at 10 seconds, maybe it's down to, 90 grams, right? We know that the mass is changing. I thought there's mass conservation. It would have been conserved if we were in a closed system, but we know this time, anytime that there is a change in mass, the change in mass is actually mass of CO2 escaping. So even after the reaction is done, this is not going to eventually hit 0. It's not like the beaker sort of suddenly vanishes on you, but we can track the relative change here. This mass here is the mass of the total system. It's the beaker plus the solution plus the calcium carbonate plus everything there. Any change in mass, however, is attributed due to one chemical, and again, it has that nice feature of 1, and therefore we can do some stoichiometry and we can go re-express in terms of other chemicals. So in this case here, this is probably the easiest setup here, allows for continuous readings. So as the mass steadily decreases, allows continuous readings, so mass versus time can be plotted. Right? So although we may be just sampling it at a couple of specific times here, once I plot a graph, we have y versus x. We're going to do this a little more detail on the backside here, mass versus time here. I can track the gradual change in the mass over time, and I know any difference due to the mass is because of carbon dioxide. So specific to carbon dioxide, we can use molar masses. This one here, just a technical note, when they've tried to do this, this one here works well for heavy gases. Gases that have slightly larger molar masses, things like CO2, things like oxygen. It doesn't work as well for hydrogen. Not that the mass wouldn't decrease, but the rate of reaction that we're getting and how much hydrogen that you're releasing off, maybe it's not going to make a substantial change until you wait really, really long periods of time. Right? Okay, so far we're looking at rate. Both of these have been continuous because I can just sample it as the reaction occurs. In this third one here, we're going to want to watch how does concentration actually change in time. In general, it's really hard. We don't have meters that detect every single possible, I want the concentration of zinc changing or concentration of iron changing. I don't have meters for every single chemical for concentration. So concentration needs to be used in a very specific fashion or very specific chemical. Essentially, the idea is the same. We're going to measure either the reactant concentration or the product concentration. Once I know one of them, I can just use stoichiometry to get to the other one. we're going to measure it at certain time intervals. I'm going to pick out a couple time intervals to choose from. And how we're going to actually find concentration in part C here, we're going to do it by titration. So if you remember, titration was your lab where we had one solution in the burette. The other solution here is in the Erlenmeyer here. And basically what we did is we slowly figured out, well, how much volume do I need to drop in before the indicator changes color, before I hit that equivalence point? That's when I know to stop. Now, definitely, you cannot do this in real time. You can't be like, oh, at 5 seconds, do a really quick titration. And then at 10 seconds, do another really quick titration. How this one here would end up working, although we are using a titration, what we're titrating is we're titrating it against freeze frames of the reaction. So titrating against freeze frames of the reaction. So let me just hint at how this reaction occurs. Let's take a sample experiment. I'm going to take hydrogen peroxide, H2O2. It's going to react with 2H plus and 2I minus in becoming I2 and 2 waters. All right, so there's the reaction. I'm interested in studying how fast this reaction occurs. What I want to emphasize in this example reaction here is you'll notice H plus is a reactant. That means this reaction requires acidic conditions. If you're not acidic, this reaction cannot occur. So here's what I'm going to do. I'm going to start off with some hydrogen peroxide. You can even have the hydrogen peroxide and the iodide in the same container. Those are the other two reactants. But without the acidic conditions, this is simply not going to react. So what you're going to do here is you're going to add in the H plus when you're ready. When you add in the H plus, you provide the acidic conditions. That's at 0 seconds. You probably know how much you added, so you know the starting amounts. And what you're going to do is you're going to run this for a set time interval. So let's say I run this for 1 minute. So the reaction has been going on. Some of the reactions, it's been producing iodine and fresh water here. So I let the reaction go for 1 minute. And what I do at that point there is I end up tossing in some base. Let's toss in, I don't know, baking soda, sodium carbonate. And what's going to happen there is at 1 minute, maybe the reaction wasn't quite done. But what the sodium carbonate here base is going to do, the base is going to kill off all the H plus that I have. Maybe based on my amounts, I'm going to ensure that the Na2CO3 is actually in excess. Essentially what I'm doing here is I let the reaction go for 1 minute by adding the base. By killing off the H plus, I've essentially taken away the acidic conditions. Without that ingredient, we've now limited the reaction. The reaction is now stopped. And now what you can do is you can do a titration. You can actually find the concentration of iodide. So even though a titration may take a little bit of time, you can actually sample by 1 minute of time how much iodide did I have left. What I can do later is I can set a beaker to have reacted for 2 minutes or 3 minutes or whatever time interval you want. Essentially what's happening here is I'm tossing in the base at different time intervals. I'm cutting the reaction off at a specific time, and then I'm running it through a titration to sample the concentration, and therefore I can still end up plotting. If I was tracking, let's say, the concentration of iodide with my titration, I can still say at 0 minutes, we started off with the maximum reactants. I would imagine it starts out high. At 1 minute, although we had to do a freeze frame, this 1 minute reaction was sort of stopped, frozen in time at 1 minute. I did a titration to figure out the iodide. I'd expect it to be less. At 2 minutes, I expect it to be less. 3 minutes, I expect it to be less, so on and so forth. I'm still able to plot the change in concentration versus change in time. That's why I need for a rate of reaction. But you had to do it not continuous readings anymore. This one here is more of a freeze frame picture of it. Right? Onto the backside here, we're going to see a couple of different ways. What you're going to find is, depending on which reaction that we're looking at, you might be able to do mass change. You might be able to do volume change. You probably won't be able to do all of these for every single reaction. So choose one that's convenient for you, that's easy for you. When we do part D here, we're looking at a change in color versus change in time. We're tracking a change in color intensity. If you remember back in our chapter 3, we essentially was measuring absorbance versus a whole bunch of different lambdas here. We send in the whole Roy G. Biv. Remember, the red side is a 700 nanometer. The purple side is a 400 nanometer. If my solution so far looks green, remember, it's not because it's absorbing green. We have to use that color wheel here, Roy G. Biv. If it's appearing green, green is actually the complementary color. What's actually being absorbed is actually a red color. So there's a red color that's absorbed, so that what we're seeing is actually our green color as a complement, green complement reflected. And if it's due to a transition metal ion, let's say, for example, they're using iron. Iron is actually not green, but if it's due to a particular chemical that's actually giving you the coloration as the reaction occurs. In this reaction, I know that this FeSCN actually is a really, really deep red color. So as I produce more and more of this FeSCN, it's actually going to get more and more red intensity. Essentially, as I then scan in the opposite wavelength, I would actually send in green for a red solution like that. What I'm going to track is as I produce more and more particles that are willing to absorb the complementary color, the absorbance is going to steadily change, and basically what you're going to end up with is you're going to have a absorbance versus time graph, right? Track how does the absorbance change. At first, maybe I didn't have a lot of the FeSCN. This one here by itself, again, is a deep red color. Maybe there's not a lot of absorption to begin with, but over time, as I generate more and more of this one here, it's going to absorb more and more green color, and basically it's going to start climbing that way. That's also a measure of concentration. Aside from those two methods, one with titration and one with spectrophotometry here. This one here, let me just remind you the term. This guy here is called the spectrophotometer. It's really hard to identify concentration. Just for completeness sake, however, here, we could do one more that's concentration. You may have seen these pH meters before. So pH meter, we're going to learn a whole chapter on acids and bases, and basically pH is this ruler. At 25 degrees, 7 is the dividing line. Depending on, let's say in this reaction here, we actually used up H+, we're slowly getting less acidic. Remember, the most acidic is actually the farthest away from 7. If we're actually getting less acidic, so less acidic, we actually use the phrasing here, pH increases. Now, a lot of people get that wrong here. They say, pH, we're watching H+, it's an acid scale, right? In this case here, it just depends. pH is just a ruler. If I go from a pH 0 to 1 to 2 to 3, the pH, the number is actually getting bigger, but because I'm getting closer and closer to the neutral, it's actually getting less acidic. Those are probably the three ways I can think about that can track a concentration change versus time. Other than that, you don't have meters that read how much zinc is there, how much iron is there, how much copper is there, right? These are the specific ways that we can actually do concentration against time. So let me just finish up with the color change here. This one here also allows for continuous readings. We don't need to do that freeze frame again. Allows for continuous readings because as I produce more products, or even maybe the chemical on the left side is the thing that's being colored, as that gets used up, the absorbance will drop. Allows for continuous readings. Plotting, you can either plot absorbance or percent transmittance. Those two are sort of inverses of each other here. What doesn't get through is sort of absorbance. Percent transmittance will be low and vice versa. We're going to plot absorbance transmittance, both of these versus time. So one thing we've been seeing throughout this lesson here is it has to be something measured against time, so that way I can get a measure of how fast the reaction occurs. Right. Step E here, we can measure the change in concentration using conductivity. Right. So conductivity, what we're looking for is we're looking for charges, and we're looking for the charges to be mobile. These charges here could very well just be electrons traveling through a metal wiring. It could be ions in solution here. We can actually track a qualitative conductivity depending on the charges that I have. So, for example, for that reaction here, let's take bromate. Let's react it with 5Br minus. It's going to react with 6H plus. That one is also requiring acidic conditions. 3Br2 and 3 water here. We'll notice over the course of this reaction, we go from having a ton of charges, right? Bromate, bromide, H+, they all have charges. Suddenly going into the neutral form of bromine, suddenly there's no charges anymore. So what's going to happen is over the course of time, maybe with all these charges here, it was enough to run a light bulb. As the light bulbs here steadily dims, I'm actually losing the ion concentrations. The chemicals are still there, but they're being converted into a state that they're actually neutral. In this case here, we're actually just track the decrease in concentration of ions. Now this one here is not as good because I'm not specific to is it the bromate that I'm losing or the bromide or the H+. This is just in general. I'm losing charges against time. Decreased concentration of ions lowers the conductivity. It makes the solution here less and less conductive. It doesn't carry a current as well. Right? So we've seen a couple different ways here. That one flows really nicely with our main definition. To measure the rate of reaction, we're tracking the change in reactant concentration as it gets consumed, or the change in product concentration as it gets picked up. Just for completeness sake here, they're going to refer to these ones here as clock methods. There are very specific reactions where we call them clock reactions. We're going to see an example of them later on in this unit here. But basically, a clock reaction here, it's set to be in equilibrium. So let's say I have chemical A, and I have in equilibrium with chemical B. So basically, over time, A is going to become B, and after a while, B is going to become A. Usually, clock reactions are nice when there's actually color change associated. So let's say A is colorless, and let's say the B is actually blue in solution. So what's going to happen in this clock reaction is it's going to stay colorless. As the reactants are allowed to react, they start forming B, which is the blue color. So suddenly it turns blue. After a while, this blue color, as it reacts here, it then reacts and reforms A. As I lose that blue coloration here, it turns colorless again. This is going to switch back and forth between blue and colorless, blue and colorless. Usually what you would do, once you mix the solutions and as the reactions are going, usually you let the color change go back and forth a little bit. And what you can do is you can sample, well, in 5 minutes, how many times did the color change go back and forth? And I can just sort of average it out. Well, if it changed colors 5 times back and forth in 1 minute, I can say, oh, one color change took, what is that, 1 minute divided by 5, 12 seconds, right? So in this case here, clock method, again, it doesn't allow for a continuous reading. This time here, it only gives an average rate over a certain time interval. Even if you just look for one color change back and forth, it's only an average. It doesn't really get into the details of who's actually colliding, how many steps is the reaction actually taking, but it's just saying overall, hey, the color changed this many times, we can just go 1 over time to find the rate, and therefore we can say the reaction time, again, is inversely proportional to the rate. All right. So those are a couple different ways of looking at rate, just monitoring the rate here. We talked about taking readings either continuous or in that freeze frame kind of analogy here. What's really helpful, even though you may only be taking readings at a couple instances in time, what you can do is you can actually graph the data. So once you've chosen this technique here, you can graph the property. Maybe it was concentration. So we did concentration via titration, concentration via spectrophotometry, concentration via conductivity, right? Somehow you have some measured value. So maybe this is a change in concentration. In this case here, because this one here is climbing, I would imagine that this is a product because the product is being created. If the same line here, if it's dropping, I would imagine that's reactants, and this is the one mathematically that it usually comes out as negative. So even though in general we say rate by definition is a change in product concentration versus time, again, just to be complete here, this top part may or may not actually be a concentration. Maybe I decide to do a change in mass instead. So maybe my measured quantity here is actually the total mass of the system, right? Maybe in the open system here, I started off, I would label my axes. So I have mass, this is actually measured in grams. I have time measured in seconds. And overall, what's happening here is I start off with my maximum amount of reactants. The mass is very, very heavy. If I then release off a gas and that gas is allowed to escape, I may have only sampled it at 0 seconds. That was my mass. A little bit later, this is my mass. A little bit later, this is my mass. I sort of get a track of how this thing here changes in a continuous reading. What we want to do then is we want to find the rate. The rate is the change in mass over change in time. Let's just pick any 2 points here. To find a change in mass, what you would do, well, mass is actually along the vertical axis. A change in mass is actually given by the rise of this calculation. For the change in time, because time is actually on the x-axis, that's actually going to be a run. Mathematically, what we've done, when you do a rise divided by run, this one here, the rate can actually be given by the slope of these curves. Now, when you do slope, this rise over run, sure, if you have coordinates, you can do y2 minus y1, x2 minus x1. There's actually 2 different types of slope I can measure for you. First one here is sort of an average slope. We know that looking in detail here, at first I have the most reactants. So at first, all these reactants here can collide with one another here. I'd imagine the rate here starts out pretty fast. So the slope is really, really slanted. It's actually a negative slope to imply that this one here is actually being consumed. Over time, as the reactants start getting eaten away, I have less particles that can collide, less particles that can collide. You'll notice what's happening to this tangent here is it's steadily getting flatter and flatter, right? So even though we were sort of, in this case here, because the slope is really steep here, we can say it was fast at first. But as I steadily use up the reactants, we gradually slow down. We gradually get to a point where the slope is pretty much flat. What I can ask you to measure is I can ask you to measure two different rates. First rate, the easier rate here, is just called the average rate, like we did in this clock reaction here. For an average rate, what you're going to do is you're going to take the slope of the secant. And the secant line is basically a connect the dot line. Even though this reaction rate here, it was fast at first and it slows down as time proceeds, it eventually loses a total of this much mass, all the mass there, and it takes this much time. So if I just take a point here as it starts leveling off, I know I need to lose this much total mass in this much time. If instead of being fast and then gradually slowing down, if I just connected the dots, if I travel from point to point just with a constant slope, we should use a ruler for there, with a constant slope here, what average speed would I actually need to have to actually get from this change in mass to this change in time? So you see it sort of averages out. Yeah, it's actually, this slope here is actually going to be a little bit slower than the steepest. It's going to be a little bit faster than the more shallow. But this one here, if I just took a reading at the beginning, if I just took a reading at the end, what constant slope would I have to go at to actually get the average speed? In that case there, the average rate would be the slope of this line that I gave you. That line is called the secant. That one's not too bad because we actually have 2 points. I have my coordinates. I can do y2 minus y1, x2 minus x1. The challenge is, what if I am interested in an instantaneous rate? What if I don't want you to just sort of gloss over and sum over, yeah, some are fast, some are slow, here's the middle value. What if I really want to know, well, how fast is it going at the beginning? At the beginning here, in general, you can refer to this as an instantaneous rate. That is the rate at a given instant in time. In this case here, the instantaneous rate at 0, in particular, is called the initial rate, right? That's the beginning rate. We're actually going to make use of initial rates later on in this chapter as well. This time what I want to do is I actually want to find, nope, don't average it out. I want to know the real steepness of this really first part of the curve. Only problem is because I only have one time interval, I only have 0 seconds, I only have 1 point on the curve. And you've seen what we actually did here, if I can just zoom in there. As I zoom in there, the curve itself may have followed some sort of trajectory there. At 0 seconds, I had a singular point here. I can't take the slope of a singular point. What you actually want to sketch in here is you actually want to sketch in a line called the tangent line. A tangent line is a straight line, touches the curve only once, and the hope is if I zoom in really close to this tangent line and what the curve is doing, I'm hoping my tangent pretty much overlaps with the curve itself. Once you have the tangent line here, that slant is fixed, then you can choose any 2 points that are easy to read on the tangent. I'm imagining that you had this on grid paper here. Pick any 2 points, find the slope of that tangent there, and that slope there would be the instantaneous rate. So this is the slope of the tangent at whatever time interval you're wanting. If I do at 0 seconds, it's called initial rate. I can find what's the instantaneous rate at this second time interval. All you do is you just prop a tangent line there and basically read 2 points that are easy for you. We can just note down in general here, we know that the rate is actually not constant over the time period here. How come the reaction rate changed? In this case here, the reaction rate decreases as the concentration of reactants are consumed. We're going to actually come back to this in a later lesson here. Basically, reactant particles need to collide together. As over time, at first I have a ton of reactants here, lots of collisions can happen, lots of reactions can occur, but as over time the reactants start falling away and dropping away, we get less and less going on. So let's just deal with a numerical example here just to finish off. Let's consider the following reaction. So they specified a reaction. We can think about what sort of properties I can measure. Well, we are releasing one gas. We can measure this as a change in mass over change in time. I can hook it up in a closed system and use a syringe to take continuous readings. They've done that. And what they've actually figured is the rate of production, the rate of making O2 is actually 3.25. They've put us back into our generic units, which is helpful. Mole per dm cubed, that's your molar, all over a second. That's the rate at which the oxygen is being formed. And all they want you to do in this problem here is just see if you can do a stoichiometric conversion. Get from oxygen, can you re-express it in terms of N2O5? N2O5 is actually a reactant. Reactants instead are being consumed. So here we go. We want to find the rate of N2O5. So how many moles of moles per decimeter cube? It's a concentration. It's an amount in total of N2O5. Do I produce per second? They didn't specify any other unit, so that's what they want. Let's start off with what we're given. We're given 3.25 mole per dm cube. This is talking about oxygen. This is produced per second already. And all we're going to have to do is we're just going to use the mole ratio. My balance equation says when there's a 1 in front of oxygen, there is a 2 in front of N2O5. So 2 moles of N2O5, and you just double that there, and this one here gives you 6.50. Keep track of your sig figs and all that. And now we've been able to re-express. The speed has exactly been the same, but why is the number different? But this number here is now referring to 6.50 mole per dm cube per second, but it's looking at how quickly the N2O5 gets used up. Mathematically, you could put a negative here. You could start adding negatives, taking away negatives, but all that negative reminds you is it's being consumed. You can actually use as a positive number the rate at which N2O5 it's being eaten away is positive 6.50 mole per molar per second. Right? So there's a couple more questions for you to just finish off here. Just careful, sometimes they might ask you when you're converting the rate here. They still kept things pretty simple, sort of molar per second, molar per second. If they end up going molar per minute, then you just set up your unit conversion and get rid of that seconds there. If they eventually ask you gram per second, then you need to use molar mass, but it should be pretty simple, just stoichiometry for you to work out there. If you know the rate of reaction, you know sort of how quickly the speed at which your chemical is actually being used up. This is the rate. If I multiply the time, I can then find the mass again. So for example, if I was hinting at part A here, I want to figure out how much mass of aluminum is produced. So aluminum is a product in this equation here. I actually let 5 minutes go by. Unfortunately, my rate is actually in gram per second. So here's what I mentioned earlier. 1 minute is 60 seconds. I can multiply time by the rate that they give me, 0.050 grams per second. This also is a rate, even though it's not technically a concentration over time. We're sort of tracking the amount using mass in this case here. You see all the other units die away, and we end up getting how many grams actually ends up forming. So if I know the time and the rate, I can just sort of rearrange it. So far we had rate. In this question here, we have rate is change in mass over change in time. If I bring the time up, the time, how long I wait, multiplied by the speed at which it gets produced, is actually going to give you the overall mass. Make sure you do question number 4 here. They sketch out a nice graph for you here. We note this general trend here. We're tracking a change in concentration of acid. So maybe I've done this using a pH meter here. Calculate the initial rate. They want you to sketch in a best fit line. Basically, we take all these readings here so that we can get a sense of what the average should be. The initial rate will be the slope of the tangent. So part A, you use a ruler here, draw a nice straight line here, try to find the slope of that one there, find the average rate over 0 to 100 seconds. If I sort of erase over there was fast and then gradually slows down, if I just used a ruler here and I just said, well, if I want to lose 1.2 molar worth of concentration and it took me 100 seconds, on average, every second, how much did I lose? That would calculate average rate. Likewise, instantaneous rate at 50 seconds. Pretty much if they only give you one time interval, you're using a ruler here and you're sketching a tangent line. The tangent should basically follow your curve just at a single point here. Your tangent might be different from the person next to you. That's why in this case your answer may vary. But what you want to do is you want to calculate the slope of the tangent that you wrote. All right? So we'll pick it up from there tomorrow. If you have any questions, just let me know. Thanks, guys.